Let us begin very gently with a question that seems almost physical before it seems mathematical. Suppose we take a metal rod and heat one end of it. At first, the warmth is concentrated near the place where the flame touched the metal. But after a while, the heat begins to spread. The hotter region shares its energy with the cooler region beside it, and that region shares with the next, and so on. Slowly, steadily, the distribution of heat changes along the rod. This is a very ordinary phenomenon. It belongs to everyday life. We feel it in a spoon left in hot tea, in a radiator warming a room, in sunlight absorbed by a stone. And yet, hidden inside this simple process is one of the great ideas in mathematics. The question is this: how can we describe the changing pattern of heat in a precise and intelligible way? At first glance, the pattern of temperature along a rod can be very complicated. One part may be very hot, another only warm, another still cold. The shape of this temperature distribution may be uneven, irregular, and not at all simple. So the mathematical challenge is immediately clear. Nature gives us a state that is complicated. We would like to understand its evolution. We would like to predict what it will look like later. And for that, we need a language in which complexity can be broken into simpler pieces. This is the beginning of the story of Fourier analysis. It is worth repeating. The original motivation was not abstract symbolism for its own sake. It was a physical problem of heat. Mathematicians and physicists wanted to understand how temperature spreads through matter. They wanted to know how a complicated state changes with time. They wanted to discover whether there is some deeper structure hidden beneath the apparent complexity. And little by little, a remarkable answer emerged. When we try to understand heat flow in a rod, one natural strategy is to look for especially simple patterns. Instead of trying to solve the whole complicated problem at once, we ask whether there are basic shapes of temperature distribution that behave in a clean and predictable way over time. This is a very important style of thinking in mathematics. When a system is complicated, one often looks for building blocks. One asks, are there elementary patterns which the system treats in a particularly simple manner? If so, perhaps a complicated state can be assembled from those elementary patterns. For heat flow, the elementary patterns turn out to be wave-like shapes along space. Not waves moving back and forth like water on a pond, but spatial patterns that rise and fall smoothly along the rod. Some have one broad hump, some have several alternating humps and dips, some very slowly, and others very rapidly. These repeating patterns have a regularity that makes them mathematically manageable. Let us pause and reflect on that. The rod may begin in a very messy temperature state, but instead of staring at the mess directly, we try to express it as a combination of simple spatial modes. Each mode is like a basic pattern painted along the rod. The overall temperature is then imagined as a layering of many such patterns on top of one another. This is already a deep conceptual shift. Instead of asking only, what is the temperature at each point, we begin asking, how much of each basic pattern is present? That second question sounds different because it is different. It moves us away from direct physical location and toward a more structural way of thinking. And the astonishing fact is that nature seems to cooperate with this strategy. Why do these smooth repeating patterns matter so much? Because physical systems often possess what we might call natural modes. A stretched string does not vibrate in a completely arbitrary manner. It has preferred patterns of vibration. A column of air in a pipe has preferred standing patterns. A rod conducting heat also has preferred spatial patterns that evolve in especially simple ways. This is where the familiar wave shapes, the ones associated with sines and cosines, enter the story. They rise not because mathematicians arbitrarily chose them, but because they fit the structure of the physical problems. They are adapted to repetition, oscillation, and boundary constraints. They are the natural language of many systems that involve balance, propagation, and smooth variation. In the setting of heat, these patterns do not travel like sound waves. Instead, each pattern simply fades with time. A broad smooth pattern fades slowly. A rapidly oscillating pattern fades more quickly. So if the initial heat distribution contains many fine wiggles and irregularities, those fine details tend to disappear first. The roughness dies away faster than the large-scale structure. This is a beautiful idea, and it is worth repeating. A heated rod can be described as a combination of basic modes. Each mode has its own spatial shape. Each mode evolves independently in a particularly simple way. And in the case of heat, that simple way is decay. Every mode fades, but not all at the same rate. The more rapidly varying modes usually fade faster. That is why heat flow smooths things out. It removes sharp distinctions and preserves broad trends longer. So now the complicated physical process becomes more understandable. We do not need to follow every point in a brute force way. We can decompose the initial temperature state into modes, let each mode fade according to its own rule, and then recombine them. Complexity is handled by decomposition and recombination. This was one of Fourier's great insights. He proposed that even very complicated states could be represented as sums of simpler wave-like components. This was a daring and transformative idea. It suggested that a function, even one that seems irregular or awkward, may be understood as built from a family of simple oscillatory ingredients. Today, this seems natural to many students because Fourier analysis is now everywhere. But historically, it was a profound reorientation of thought. It asked mathematicians to believe that irregular phenomena could be encoded through orderly superposition of basic waves. And this did not concern heat alone. Very soon, the same viewpoint revealed its power in the study of sound. When we hear a musical note played by an instrument, the sound reaching our ear is not usually a single pure oscillation. It is a blend. There is often a basic tone, which gives the main pitch, along with higher accompanying tones that enrich the sound. These higher components are often called harmonics. They shape the color or timbre of the note, the quality by which a violin differs from a flute even when they play what we would call the same pitch. So again, nature presents us with complexity. A real sound is not simple. Yet Fourier's viewpoint tells us that this complex sound can be analyzed into simpler periodic components. One can ask how much of the fundamental is present, how much of the next harmonic, how much of the next, and so on. This is strongly analogous to the heat problem. In the heat problem, a complicated temperature distribution is decomposed into simple spatial modes. In the sound problem, a complicated tone is decomposed into simple frequency components. In both cases, the central move is the same: break a complex object into basic wave-like pieces that the system understands naturally. It is worth pausing here because this analogy is one of the most important points in the whole story. Heat and sound seem like different phenomena. One is about temperature diffusing through matter. The other is about vibrations transmitted through air or material. One smooths and fades. The other oscillates and resonates. And yet both lead us toward the same mathematical architecture. Both point us toward the idea that wave-like modes are the right coordinates in which to think. This is exactly the deeper lesson. Fourier analysis was not merely a trick for one problem. It uncovered a general principle. Many physical systems become clear when expressed in terms of their natural modes. Let us say that again in a slightly different way. A function can be studied directly, point by point, in physical space. For temperature distribution, that means thinking about the rod itself and the temperature at each location. For a sound signal, it means thinking about the pressure variation at each instant of time. But one can also study the same object through its frequency content, meaning through the strengths of its basic oscillatory components. That second viewpoint is what people often call frequency space. Frequency space is not another physical room somewhere. It is another description. It is another coordinate system for thought. In physical space, we ask where something is happening. In frequency space, we ask what oscillatory ingredients are present. These are two complementary ways of understanding the same object. This shift was revolutionary. Before this way of thinking became standard, one might look at a function only as a graph or as a physical profile. Fourier analysis taught mathematicians to hear structure inside a function, almost as if a shape could be treated like a chord in music. A complicated curve was no longer just a curve. It became a combination of frequencies. A signal was no longer just a signal. It became a spectrum of contributions from simpler modes. This language now feels so natural that it is easy to miss how conceptually powerful it is. Fourier's work linked geometry, physics, and infinite series in a new way. Geometry enters because the patterns have shape. Physics enters because the patterns arise from natural phenomena like heat conduction and vibration. Infinite series enters because one basic pattern is usually not enough. We need many of them, possibly infinitely many, layered together to represent the whole state. So the mathematical object is not only a single smooth wave, but a superposition of many waves. Some contribute broadly, some subtly. Some dominate the large structure, others supply fine detail. Taken together, they reconstruct the original function. Again, let us pause and reflect. A complicated function may be understood by taking it apart into simpler wave-like constituents. Each constituent has a clear identity. Each is mathematically tractable. The whole is reconstructed by summing them. This is the heart of Fourier analysis. And once this idea was accepted, mathematics changed. It became possible to approach partial differential equations with a new confidence. A partial differential equation often describes how a quantity changes in space and time. Heat flow is one example. Vibrating strings are another. Waves and fluids, quantum systems, electrical signals, all these eventually enter the picture. Fourier methods allow one to transform a difficult global problem into simpler component problems. One solves for the behavior of the modes and then assembles the result. That is why Fourier analysis became foundational in the study of partial differential equations. It provided not just formulas, but a way of thinking. It suggested that the right path to understanding a system is often to find the basis in which the system becomes simple. And the influence did not stop there. Signal processing, acoustics, electrical engineering, image compression, communications theory, control theory, and many branches of applied mathematics all inherited this perspective. Whenever a signal has hidden oscillatory structure, Fourier analysis becomes relevant. Whenever a system responds differently to slow variation and fast variation, Fourier analysis becomes relevant. Whenever decomposition into modes reveals order inside complexity, Fourier analysis becomes relevant. In sound engineering, one studies the frequency content of audio signals. In image analysis, one studies spatial frequencies that correspond to broad features and fine textures. In physics, one examines normal modes, resonances, and spectral behavior. In engineering, one filters signals by removing or amplifying certain frequency bands. Everywhere, the same conceptual move reappears. Take something complicated. Decompose it into elementary oscillatory pieces. Understand the pieces. Then understand the whole through them. It is worth repeating because it is so central. Fourier analysis became powerful not because mathematicians enjoyed complicated series for their own sake, but because nature itself often organizes complexity through waves. Heat patterns can be decomposed into modes. Sound can be decomposed into tones. Vibrations occur in natural forms. Signals carry layered frequencies. The mathematics succeeds because it matches the architecture of the phenomena. And there is also something philosophically beautiful here. At first, the world may appear noisy, irregular, and resistant to understanding. But Fourier's insight suggests that beneath the apparent disorder there may be an underlying harmony. A complicated state may contain hidden regularities. These regularities are not always visible in ordinary physical description, but they emerge when we look through the lens of modes and frequencies. So one of the deepest lessons of Fourier analysis is not merely computational. It is conceptual. It teaches us that the right representation can transform our understanding. A problem that looks tangled in one language may become transparent in another. Let us pause and state the central shift very plainly. Before this viewpoint, one might say, here is a function, and I study it where it lives. Along a rod, across an interval, through time. After this viewpoint, one also says, here is the same function, and I study the mixture of frequencies from which it is built. That is the move from physical space to frequency space. And this move does not destroy the original picture. It complements it. One can pass from one viewpoint to the other. One can think of a signal as a shape and also as a spectrum. One can think of heat as a temperature profile and also as a mixture of decaying modes. Both descriptions are real. Both are useful. But often the second reveals the hidden simplicity. If the listener has drifted a little, this is a good moment to gather the thread again. We began with heat in a rod. The problem was to understand how temperature spreads. This led mathematicians to search for simple spatial patterns that evolved predictably. Those patterns were wave-like modes. Each mode faded over time in its own way. A complicated temperature distribution could then be viewed as a combination of such modes. From there, we turn to sound. A musical tone is not usually a single pure oscillation, but a combination of a fundamental and harmonics. Once again, complexity is described through simpler oscillatory parts. From these examples emerged Fourier's great insight. Many complicated physical states can be represented as sums of simple wave-like components. This linked physics geometry in an infinite series. It transformed the study of partial differential equations, and it introduced a new conceptual world where one studies not only where something is in space, but also what frequencies it contains. Now, as we move toward the end, let us slow down and unify the picture one last time. Heat and sound were not just examples. They were gateways. Through them, mathematicians learned that nature often speaks in modes. A rod cools through decaying spatial patterns. A string vibrates through standing wave patterns. A sound resonates through a family of harmonic components. What seems complex in ordinary observation often becomes structured when resolved into its wave content. Fourier analysis is the mathematics of this resolution. It listens to functions. It separates blended behavior into elemental oscillations. It reveals hidden architecture inside profiles, signals, and solutions of equations. It gives us a way to move between the concrete world of positions and times and the more structural world of frequencies and modes. And perhaps it is the most soothing and enduring thought in the whole subject. Nature is often complicated, but not always chaotic. Very often, its complexity is organized. Very often, it can be unfolded into simpler patterns. Very often, waves are the secret grammar beneath the surface. So the big takeaway is this: Fourier analysis became powerful because the world itself so often arranges complexity through waves. Heat led mathematicians to discover this. Sound confirmed it. Physics amplified it. Mathematics gave it precise form. And from that meeting of physical intuition and mathematical structure, an entire field was born. Let us end with that image resting quietly in the mind. A heated rod slowly smoothing out. A musical tone quietly separating into harmonics. A complicated function, no longer opaque, but made of hidden frequencies. A new way of seeing, and also a new way of listening. And from these simple beginnings, a vast mathematics opened.